So resistance and powering of ship. So this is the book cover and the chapter on resistance and powering. We already coming over to the middle of the textbook, and I will cover up to ship resistance and power estimation. You see that. And ship is big, right? The probably biggest one, around 500 or 500 meters. That is, looks like a bulk carrier or not container ship. Container ship is this one. It's about 400 meters. This one is a building up. This is a bottom. This was the tallest building in Korea until several months. Now, Lotte has a taller building. But this one is smaller than this one, right? Also, the probably Airbus 380 is bigger than this one. But you see that this is one of the biggest airplane. Still small, right? Still small. This is a 400-meter drawn upon the KAIST map. This is a main administration building where the president of the KAIST is located and all the offices for administration. Main gate is here. This is a buildings of mechanical engineering, aerospace, and nuclear engineering. There is a playground, soccer play, and baseball. So this is big. Right? Now we are around here, right? So ship is big. So how can we estimate the resistance and power, horsepower for that ship engine? And the larger the size of the ship, the big ships, the higher the transportation efficiency. Because volume is proportional to length, cubed, right? And resistance is usually proportional to surface area of the ship. So area is proportional to second order length. That's why bigger, more tons, then resistance increase. Right? Still, resistance is increasing, but increase of volume or capacity is much faster than resistance. That's why transportation efficiency is higher for big ships or big transportation. Okay, and then testing, prototype for testing is not available for big buildings and dams and tunnels and ships too, right? Because it's too much cost. Comparing to mobile phone, you can make hundreds of these prototypes before mass production. And testing real device, right? Submerged or brake or heating, many things. In case of a car, still they make full-size prototypes, several of them, not hundreds, probably less than 10 full-size prototype for testing for many things. The most important thing is performances, safety, right? The other thing. So pre-production prototype for testing cannot be built for large ship, large something, large building, large dam or tunnel, or nuclear power plant too. Nuclear power plant here. Right? The first prototype will be the final product. So we need to have only way to estimating the performance is scaled down model. You see that outside, that is still big, right? But that is scaled down. Scale factor is around 30 or 50 something. Scale down. Scale down model testing. Right. This one is the gate of this building, right? Just outside. The name is Esso Osaka. You can see the details here. Panel is there, right? Length is 300, breadth 50 meter, depth 22, power 35,000 horsepower. Speed is low, right? 15 knots. So it's an oil tanker. Displacement and power weight ratio. This is a transportation efficiency, something. And because this is a oil tanker, the submerged part is bigger than above the surface. So you should assume that submerged body. How can we predicting the speed of the ship? Used to be all art and no science. Is it something coming toward the science nowadays because we have more and more computer simulation tools and also experience or data coming from sea trial of real ship and model test. So we using such big data, and also computer simulation together, we have more and more science or predicting. Still, it is predicting, not calculation, prediction. So it's tough. But you should guarantee by contract, right? Guarantee the speed. So you need some margin, safety factor to guarantee the speed, right? We still have a difficulty in predicting the resistance of a given hull from at any given speed. Yeah, there is guaranteed speed. Right? Viscous various methods based on sound principles are available. Yes, there are. But however, the numbers are derived from empirical. Empirical means from data, previous experience, data coming from previous project, not this one. And model test, and all existing old ships. Right? Additional difficulties are hard to predict influences such as sea conditions. In the real sea, there is a wind, wave, and current. So it's not easy. Especially if you're trying to make say final testing together with the owner who ordered the ship, you should show the guaranteed speed, right? At the sea. Well, how can you measure? Because there is a wind, there is a wave, right? But guarantee speed. So measuring also sea trial is not easy also. There is a standard way of doing such trial conditions. Loading condition. Loading condition is how much cargoes are loaded onto the ship and where, and which kind of cargo. There is complication. So only if you are talking about containers, there are empty containers too, and heavy containers, light containers, half full containers. So loading condition is still complicated. And fouling is rust or painting, skin condition of the ship. Because of the rust of the steel, or because of some biological additives onto the surface. So that makes complication. Resistance is one force. When you're running inside the water, you feel the forces, right? Resistance. But for prediction, for the study, for the measurement, for the model test, we divide into components. So first one, frictional resistance, then wave resistance, and eddy resistance. And air resistance is above water. So this one is above water. The other three is for underbody, right, with the water. And these two can be joined to make a, these two can be added to have a name for residual resistance. So by dividing two parts of whole resistance, total resistance is frictional and residual, right? And residual is still further divided into wave making and resistance, eddy resistance. Okay. For the submerged body, submerged is something like a submarine. There is no wave making resistance, right? No wave making resistance. So only two components. One is frictional, first one, and there is no wave making resistance for submarine, right? So only the other one is, remaining one is eddy resistance, coming from this separation and turbulence and pressure. So we call this pressure drag, but viscous drag, viscous pressure. I will not explain much about this. Foam drag, we already see this one previously in another class. Right? We already see that airfoil is much less than flat plate. Right? How many times? 50 times something. Right? So shape, the foam drag is important. Foam, the shape. That's why the turtle ship and Japan ship has different foam drag. Right? Resistance and speed in the water. And Kelvin wave is very special or famous. We may see similar wave patterns behind airplane too, but not the same. This is duck swimming. Right? They also creating waves. Right? So this is wave making resistance. There are details, different waves coming from bow and stern, and also there is a turbulent wake zone. This is very pretty stable and long staying. So sometimes submarines, this is for Navy. They want to trace submarines, right? And the wake coming, even though the submarine is fully submerged, the wake field is coming in onto the surface after some time. Right? So by seeing the satellite or helicopter imaging, computer vision, you may trace the wake coming from submarines. So they are using that kind of, but the wave disappears quickly comparing to the wake, because there's a turbulence and spinning. And bulbous bow, the idea of bulbous bow is trying to canceling two waves coming from different portion of the ship. Okay? So without bulb, still they are creating bow bow waves, right? Bow waves. They are saying bow waves. Right? Bow wave. Bow wave patterns coming. But by designing the bulb, this is bulb. Bulb is simplified as an additional cylinder. Right? So coming together. So this one creates another wave. Right? Normal shape without bulb. So that can be the waves coming from these two portions is canceling each other. That is the idea. But it's not easy because the design condition, for the design condition, you can match, you can create such an ideal state. But ship is changing their draft and pitch and trim and conditions are changing, right? So it's not easy to make such ideal condition. Usually you can have a perfect full draft design condition so that can be the design point for bulb design. Right? Major resistance components. Once again, the frictional and residual. Residual is divided into two parts, wave making and eddy resistance. Right? So frictional is coming from viscosity, so you need to have a clean painting of surface without any fouling or additives. That can reduce the frictional resistance. And shape, foam drag. Foam drag is coming from aerofoil shape, right? Pressure drag. So in most ships, frictional part is bigger than residual or eddy or pressure draggers. But in high-speed ships, something like battleships, speedboat, planning hull, that can be equal or can be higher. In high-speed, more high-speed, small high-speed planning hulls. Power definitions. So we can start from engine, right? Prime mover. This is an engine. So this is braking horsepower, brake power. So if you want to have a braking, so how much force should be or torque? And after gear, there is some loss. So we have this is shaft power because from here to there is we call this long shaft. So shaft power during behind the gearbox, and there is some bearings because shaft is long. And finally, the stun tube. Stun tube is a tube that holds final bearing, and because outside is water, inside is air. Right? Stun tube is special. Is a waterproof, right? So it creates more loss, efficiency loss. And then, so just after stun tube, we call this is a delivered horsepower. And that converted into thrust by using propeller. And propeller gives you power to propel, right? And usually that efficiency of propeller is around 60% or up to 70%, but not more than 70%. And this one is same. Effective horsepower and thrust horsepower, same. Thrust horsepower is coming from propeller calculation, delivered, coming from engine to here, right? Effective horsepower is coming from you towing the model outside in the towing tank. So measuring the force you need to make the ship is running at design speed or guaranteed speed, right? How much force you need. So we call this effective horsepower. And that should be same as delivered horsepower or effect coming from the engine, right? They should be match each other. And the definition for effective horsepower is, this is resistance, total resistance and speed. Right? This is thrust and speed. This should be same. And delivered horsepower should be calculated by hull efficiency and propeller efficiency. Propeller efficiency, I told you that around 60%. 6%. There is more because of the hull. This is propeller. Say, when you're designing and testing a propeller, there are so many model propellers in the model propeller cavitation tunnel, and they test and measure the efficiency of the propeller in open water without ships. So we call this open water efficiency of propeller. We'll see in next slide again. So there is an additional term because of the presence of hull in front of the propeller. The efficiency of the propeller is different from open water propeller alone, standalone efficiency. So there is some more. So this is a bearing and stern tube and gearbox. So power estimation. So effective horsepower is coming from the towing tank. Towed force. And propulsion efficiency is from delivered horsepower, ratio between delivered horsepower and effective horsepower. So we'll see once again the picture. There's a delivered horsepower is in front of the propeller, effective horsepower. So between them is propeller, right? Propeller efficiency. So we call this is propulsive efficiency. And propulsive efficiency is made of by, this is propeller efficiency. Open water propeller efficiency. And there is a hull efficiency. Hull efficiency is because of the presence of hull in front of the propeller. Those are different, right? Because this is open water propeller efficiency because of the hull presence. So this is propeller efficiency. And there is a little bit more. I'll explain. This is negligible small numbers, but still we need to explain this. All right. Questions? And one more slide. So how can we select engine? That is important because we need to guarantee the speed, right? Because of the contract. Right? So I should design my ship and hull shape myself as a designer. Also, you need to select good engine to match the hull and engine to make a guaranteed speed at sea, right? So frictional horsepower is usually estimated by using a flat steel plate with the same area of wetted surface of the ship. You can calculate wetted surface of the ship, even though this is curved. You can calculate somehow, right? Using computer or something. Integration. So wetted surface area, you can calculate the frictional horsepower of flat plate. And then wave making horsepower. That is usually using model test. But also nowadays you can use CFD codes calculations. Anyway, you need to have somehow you need to predict or estimate those two portions of resistance. And power requirements for appendages. Appendage means can be, say, rudder, or say special fins for stabilizer fins, or other things added to that additional surface area. And some of them, we arrive at effective horsepower. That is needed to pull the ship in the sea, right? And then in reverse way, we compute the delivered horsepower coming from the engine and add some percentage for shaft thrust to get the reverse way. Right? So effective horsepower and propeller, and before then is delivered horsepower, and before then is stern tube. The stern tube, let's say, is shaft horsepower, and gear, if there is a gearbox, this is a brake horsepower, right? And then finally we arrive at sea margin, because there is waves, wind, and we also have some uncertainties inside our estimations. These are all estimations. We are not sure how much we are accurate, right? Because there is no exact prototypes, estimations. Depending on your technological skill, the margins, safety factors can be smaller, right? Smaller. So in old days it was big. Nowadays it's coming smaller than before. And then also there is a engine margin, but there is no such one. And finally you can select from engine catalogs. Big engines, 35,000 horsepower. All right. Question? No? Then we can move on to.
So, I will continue with the model Bayesian theory. So the basic idea is to predict the speed of a ship by a model test. So it was for quite a long time very difficult to predict the correct final speed for engineers until William Froude in the middle of the 19th century realized that there are two major resistance components. They are behaved totally different by scaling up from the model size boat to the real size ship. So he developed a procedure to treat the friction and the wave making separately. And he did this by understanding the laws of similitude through dimensional analysis. So the laws of similitude, this is basically how physical characteristics are affected by scale. That's the main idea. And the dimensional analysis is a procedure to formulate functional relationships between a set of non-dimensional groups. For example, you have a simple pendulum, and therefore you have the dimension of the mass, the length, and the time. You can create a function and predict the movement, the speed, and all kind of stuff of this pendulum. And to apply this to the shipbuilding, you need these physical functions. Like you need the fluid density, so basically water, seawater or normal water, the speed, the size of the body, the fluid viscosity, the gravity constant, of course, and the pressure. So, and what he did, his hypothesis is that he separates the resistance, the total, as he says, that the total resistance is the sum of the frictional resistance, CF, and the resistance of the wave making, the residual resistance. So, and there he creates, of course, a Froude number, and this number says that you can compare a model and a real-life ship when you consider this parameter. So the speed square through the gravity times the length of the ship. So, and this speed is called the corresponding speed. And when you use, when you're doing a model test and you use the corresponding speed, you have the same wave-making resistance. So it's comparable to the real-size ship. And what is the throat number? So what does it say? When you have a high throat number, you have a large deformage of free surface. So you compare it to wind making. You can easily do. So maybe talk about later. And you can affect the static pressure in relative small for planning and semi-planning ships. So, and there's also the Reynolds number for the friction in water. So I guess most of you heard about the Reynolds number before in the basic engineering classes. Basically it says that the frictional resistance coefficient CF is the same for the big ship and the model when you consider this radio. And what is the Reynolds number? So what does this number say? So when you have a high Reynolds number, you have a development of vortices. You have a rapid change of momentum by vortices. So does everybody understand what vortices is? Yeah? So, okay. And you have a high level of effective diffusion of turbulence. It's quite obvious. And now to predict the ship resistance by Freud's hypothesis, you have 8 steps to go from the real life size you want to achieve to the prediction of the power you need for your ship. So the first step is you scale your model from the real life ship by this radio. Then the second step is going to be you do a model test and measure the total resistance of the ship. Then in the third step you you calculate the friction resistance of the ship. So the friction resistance is caused by the water. And then afterwards you calculate the difference. We have some. So basically when you have the model, this is the water with the waves. First you measure the total resistance of the model, so total resistance model, and then you calculate the friction of the hull. And when you have those two, you can easily calculate the friction, the energy you lose by the wave making. So the complicated term is just these two. Yeah, that's basically his hypothesis. So in the end, quite easy to understand. And then the next step is going to be when you have so the fourth step was this calculation. When you have the residual resistance, you can rescale it to the ship size by adding the cubed cubed scale factor, and then by 6, 7, and until you have in the end the power requirement. For the friction resistance, you use a coefficient chart. So most of you know, I guess, also from the basic engineering classes. And this picture shows a model test. So, and in the end, you can extrapolate the ship resistance. In the left case, for the two-dimensional part, just the additional of all frictions. When you want to have the three-dimensional extension, you add the form factor K. Here, form factor. So when you want to have the whole ship in each direction. You also need the sideward frictions. So, and now I'm also going to tell you something about the propulsion devices. There are different propulsion devices. The most common and efficient one is the screw propeller. Like I said, it's the most efficient one. And you compare it like, you can imagine it like when you drill a screw in wood. By turning it, it goes by itself into the wood, and basically this is the same what the propeller does by a ship. By sliding the water, it makes a forward movement. There are some propeller-related terms you should maybe know. This is the suction and pressure side. So the right side of the propeller is the suction side, so where the water flows in. And the left side is the pressure side, where the force is created. Then the leading and tailing edges. So the right side is the leading edges, so this is the way the propeller turns. It's the leading edges, this is the tailing edge. Then you have the root of the propeller, the tip of the propeller, the hub of the propeller. Then the diameter is the diameter of the propeller. The pitch is the angle of the propeller when you look from the front side on it. Maybe you can see here better. And the skew is the angle of the propeller when you look from this side on the propeller. And the pitch is the distance the propeller moves with one rotation. And the slip is the distance of the theoretical movement, the pitch, and the real distance it made. So there are also different kind of screw propellers. The first one, the solid one, it's cast and machined in one piece. The controllable pitch is you can change the angle of the plates. The supercavitating propeller is designed to reduce cavitation, so I will explain this on the next slide. And the counter or contra rotor propeller, you can see it here, is very, very expensive and very complicated to build, and is basically you have two propellers on the same size turning in the opposite directions, and it's normally used for torpedoes because military has a lot of money, so they use it. And now to the cavitation. The cavitation is damages the propeller, and it's caused by a low pressure, which is created by the increasing flow speed. So when the propeller rotates, it increases it reduces the pressure around it. So when you reduce the pressure, water is bowling at a lower temperature than at normal pressure. So normal pressure, you need a temperature about 100 degrees. When you, by a high speed, it could be like 10 or 15 degrees. So the water is bowling around the propeller. The bowling creates bubbles, which disappear immediately, and by this plopping, the propeller could be damaged. And for the better understanding, I have a very short video to show you. So it's a submarine with a screw propeller. There you can see the screw. So the boiling water creates bubbles. The bubbles are disappearing and could damage the rotor blade, especially at the tip, because there's the highest speed. So, and there are also other propulsion devices, like the paddle wheels. So, like famous from old Mississippi movies. But these paddle wheels are very inefficient. and you need huge and very expensive machinery to use them. Then you have air propellers. You normally use them when you have vehicles for weed-infested areas where screw propellers would be unstable to like hit wood or grass underwater. And then there are the cycloidal propellers and magnet hydrodynamic propellers. So I will talk about them here. So first, the Voigt-Schneider propeller. It's a German invention. It's very interesting, so very different. It turns vertically around the vertical axis. And very special about this propeller is you can create thrust in any direction. So it has a lower efficiency than screw propellers, but you have a extremely high maneuverability with these propellers. And I also have a very short video to show you how they work. So they're rotating, and now you have to see which direction you want to go. First we go ahead. So they're creating a thrust backwards, so the motion is ahead. And you can adjust it in any direction. So now it's the opposite direction. So it's very useful, especially when you're at the port, for example, when you have less space for a huge ship. And like I said, you can go in any direction. German invention. And last but not least, the magnet hydrodynamic propulsion. It's still in development. Propulsion. Basically, it uses no moving part. You create a magnet field and push with this magnet field the water from the front side to the back side, and creating by this way a thrust. So the main problem of this is you need a lot of energy to create a strong enough magnet field to get a reachable, sustainable thrust. It's very expensive, and you still you need some better materials, and some more capacity for the electric. So it's like you said today in your proposal for electric ships, maybe this could be a propulsion for your ship. Japan built one prototype. You can see it here. But you see, it was like 25 years ago. Since then, nothing happens because it's very expensive, and screw propeller is so efficient and cheap that is kind of futuristic. And that's the end of my presentation. So, thank you.
Hello, I'm Dongchan Park. Today I lead the discussion session. So I prepared 3 discussion subjects. So first one is based on today's lecture. So there are 3 resistance on ships. So first one is viscous resistance. The second one is residual resistance, and third one is air resistance. So we will discuss about how to reduce the resistance. So let's talk about that ideas. Some new ideas. So it's a simple subject.
and thereby reducing residual resistance or the frictional resistance.
To reduce the friction or resistance, some painting or painting.
Yeah,
Painting material. Thank you. So you say some skin or shape? Skin? Small layer? Curve? Blocks? Some blocking design. Yeah, thank you.
Maybe for the wave making resistance, there's the bulbous bow, I believe, that cancels the waves. So I can imagine that the effect of it differs per speed of the vehicle, so maybe make it inflatable or something. Varies in size so that you can adjust it to the ship speed.
By using bulbous.
Yeah, the bulbous bow which can change in shape somehow.
Thank you.
The easiest way to reduce the residual resistance is by going by a submarine, so you can have no waves at all. And the best way to use the viscous resistance is like, for example, using a catamaran. So the lower the draft is, the lower the viscous resistance. So yeah, you have to decide what is more important for you. So yeah, and also for the air resistance. When you have a submarine, there is no air resistance in the water. But the air resistance is the smallest part. So yeah, so maybe when you care most about the residual resistance, it's really the submarine, going completely underwater, and the viscous resistance is like reducing the draft as much as possible, for example by using a catamaran or hulls.
Thank you. And any idea? Then you can move on to next discussion subject. So second one is very famous for Korean, but can be unfamiliar to foreign students. So I'll briefly introduce to you the Korean Grand Canal. The plan to make the canal through Korea, like Panama Canal. So actually, President Lee pushed ahead this project, but now the project has been cancelled. So we can discuss about this on the side pros and cons on naval perspective. So like this is Korea, and there are totally 4 rivers, and the project was originally make the canal through the river. So we can discuss about this one.
This is a canal going, I don't know, I can picture that
Yeah.
going almost from Seoul to Busan or something like this.
Yeah, it's almost.
But I mean, isn't there already some kind of train lines, like efficient train lines
Yeah.
for freight, like carrying? So what is maybe this canal is supposed to improve the flow of freight using boats. Maybe the train is not enough. So in this case, why not? But otherwise, I don't understand. If you use the train already, why do you prefer going by boat? I guess it's really expensive.
So it is not so efficient way.
I don't
know.
the actual freight capacity of the train. But I do know that there's a huge highway from Seoul to Busan and a huge train capacity, I guess. So maybe if both of them are not enough, maybe by boat, but I don't know. I don't understand why you would make it, in my opinion it does not make any sense, because the distance, you can already go there by boat. The distance gain is so minimal, it's probably even faster, because you cannot go at full speed through the canal, I can imagine. You have to go through, I don't know the English term, walks. So I think it's an enormous waste of money. I don't understand. The Panama Canal, you don't have to cross all South America, so it makes sense. But here, maybe for a hobby project or something. But
maybe the cargo carried by train come from Navy, so you don't have to move the cargo from the Navy to the train. But
you can already go by boat. It's a little bit further, but I think in terms of speed and time, it's the same.
Because the distance is too short.
Too marginal gain. I can imagine that. Maybe to improve the activity on the southwest part of the corridor. I don't know. I've never been there, but is there many activity there? I think the principal axis in Korea is obviously Seoul Busan, so it's quite only main activities. So maybe if I want to dynamize this area, but like Bart said, I don't think this is an efficient way to minimize. We can find proper ways, not using inside land tunnels, but sea channels in it. I guess. I don't know.
Yeah, it's also like Bart talked about this morning about the mega container ships. When you use them from another continent to Seoul, you have to reload the cargo to smaller ships to use a canal to go from Seoul to Busan. So it's totally inefficient. You could only use small ships, small container ships, like maybe just on the Seoul Busan size instead of the Panama size. And also you need special ships, and makes no sense.
Okay. Is there any idea? Then we can move on to the last discussion. So the third one is we are going to talk about the way to make sure the boundary. As you know, there are many troubles with China because Chinese fishing boats invade to Korean EEZ. So I just wonder that Um, in the land, we usually make the boundary by using fence or wire, but is there any idea for boundary in ocean? Can,
Sea mines.
pardon?
Sea mines.
but
Very effective, I think.
but it exists, but now still there are many troubles, so we just consider about that.
I think sea mine seems a bit drastic, but having most countries have a coastal guard patrol their territorial water, and I think that's the best way to make sure that the boundary is enforced. And maybe you can fire water cannons.
What can?
Like the coast guard, but not use force. Not like deadly force.
And is there some peaceful way? Isn't there a peaceful way? Not the military way. Politics. Any idea? No.
Is it a real problem that a lot of illegal activities happen?
Yeah. More than we think about.
Is it immigrants or illegal trade or
Illegal
what is the problem?
fishing.
Illegal fishing.
Yeah. Fishing range is.
Also, it's not really border protection, but more what happens there.
So who's fishing and
On a political level, if there's a dispute between two countries, then you can try and resolve it through diplomacy. And if that fails, I think you should go with the Coast Guard patrols.
Can you show us the video?
Yeah.
Two countries. Our defense correspondent Kim Hyun-bin reports.
Korea's Ministry of Maritime Affairs and Fisheries announced on Wednesday it will confiscate any illegal
In Seoul and Beijing last October to better secure the maritime borders in between the two countries. Our defense correspondent Kim Hyun-bin reports.
Korea's Ministry of Maritime Affairs and Fisheries announced on Wednesday it will confiscate any illegal Chinese fishing boat that crosses into Korean waters. This comes as part of the illegal, unreported, unregulated fishing agreement that was reached in last October between Seoul and Beijing. Under the agreement, all Chinese fishing boats that cross into exclusive economic zones without fishing permits will be subject to confiscation by Korea's relevant government entities, such as the prosecutor's office. The illegal boat will also be fined around $41,000 US. But when such fine is paid, the boat could still be impounded by the Chinese government if the owner does not hold proper fishing permits. Korea will also tighten surveillance on designated checkpoints in the EEZ to make sure the fish carriers are en route. Just last year, over 140 Chinese illegal fishing boats were seized. Kim Hyun-bin, Aria News.
Yeah. So this problem, yeah. There are still many troubles. So. And yeah, today's discussion. Yeah, thank you very much.